Okay, it says starting. Okay, present. Okay, so you were out there. Okay, so how do I respond to something? What do I do? Oh, oh, it just popped up. Okay, let's see. Does it pop up here? I mean, there's a chat thing there. What does that do? Group chat. List all the above. There's nothing there. I don't know what to do. Oh, enter the chat message here. Okay. And then I hit enter. Oh, oh, oh. Okay, let me go back here. Okay. So how do you, okay, wait a minute. So was it last lecture? Oh, did y'all shoot something at me or something? Oh, okay. Don't confuse me. Okay. Now wait a minute. So there's that. Is there was there you put comments on it? How do you there's a chat? But is the chat has to be live, right? Okay. Okay, so that's this box, right? But isn't this it? Well, that's no good. That's a terrible chat. That's you chatting with yourself. Go back to YouTube, okay? I'm gonna go back to YouTube. Okay, so there I am at YouTube. Is it that is that 6? Oh, is that it? Oh, okay. All right. Where do I go now? Here. I'll go to I hear myself. Ah! Okay, wait a minute. Okay, now where do I go? Okay, keep me on task here. Where do I go? What do I do? This one? Okay. But there's nothing there. Okay. Oh, okay. You just click on it. Just the one. George Bush? Yeah, but I see nothing there. Yeah. Click that one. I see nothing. No, there's George Bush live. This is okay. So why is it there and not? So do these comments get stored underneath it? So okay, and I'll be able to see them later. Okay. All right. All right. Well, there's a lot of activity now. Okay, let's move on to the lecture now. Okay, so we're in this area here. This area, not the first part of it, but the latter part is probably the most important part that you can get from the course. The rest of it you've already kind of done in a way in physics. It's just in here it gets added a little bit to it. So what I want to do is go through and put a context around this thing. So the first thing that happens is he starts in with this where, and I think we sort of mentioned this in statics, but we also had that section a bit ago in the end of the other chapter where it talks about RB, the position of point B is equal to the position of point B relative to, A plus the position of A. And if you just look at a vector diagram, you see that. You see RA and RB relative to A. This is kind of the focal point right here. Now, I know it has a weird subscript there, but there's a reason behind that. And the way they've set it up is kind of nice because of the subscripts could be canceled out. So this is kind of not necessarily dummy proof, but it's easy to make your way through this. But in addition, something very strange happens to this. The title of this section had the word rigid body involved in it. And if this little blue object here is a rigid body, I mean, most of the time it won't really be a blue object. It'll be something like a connecting rod in a car, like a big piece of metal here, in which this might be A and this might be B, or any sort of object. If it's rigid, then the distance between A and B doesn't change. Hopefully, if it did change, that means your thing broke and you've got a problem. If it didn't, then there's something very interesting you see if you're sitting on A. So this RB relative to A means he showed this before where there's a person sitting on A looking at B. The only thing that person sees is the possibility of either one, you rotating around you, or two, it just sits and goes in what he calls translation. So the object might look like this. A few seconds later, it's, well, outside of the fact that my drawing looks strange, basically you're sitting here and you're looking at that point, you don't see any change. The only other thing that can happen is you're sitting there looking at it and the thing like moved. And from this perspective, it appears as though it's rotating. And that's it. There's nothing more to it. So it's essentially this concept of, and he spends a little extra time here, and maybe he shouldn't, but he goes through and he talks about translation. Well, and then he talks about, well, if it's just purely translating, it's just moving from left to right or right to left, and it's just doing that way, then the velocity of each of those and the acceleration are the same. There's no difference between them. However, you get down and you talk about, okay, then he talks about the second thing, and that is rotation about a fixed axis, okay? He sort of diverts your attention a little bit. Maybe he shouldn't, but he starts with this, and he says, okay, and you notice that's the guy's right hand, or the right hand. It basically rotates in that direction, and actually this one should be listed first. The omega is the same thing as theta dot, and the alpha is the same thing as theta double dot. There's no difference between those at all. So absolutely nothing there that's different. You go down and he identifies those. He identifies the other one right over here. And eventually, well, he looks at this other equation, which is rarely used, but he might put a problem in the back of the book. Then he starts talking about the constant angular acceleration there. And that's kind of a byproduct of stuff you've already seen. You got to think about it like this, okay? And here, I'll do it this way, just so it's saved in the notes. See, the problem with that is that now I'm over here doing the lecture and the video is sitting over there. If I had another monitor and I could turn and look at it, that would be a little bit different. If you look at this thing, okay, and you've seen this before. He's got this equation. Well, before we started with S is equal, well, here, we ended up with this equation. Let me just write it. VT plus the acceleration constant, if it was a constant, t squared over 2. And really, I should have written the other one first. V is equal to V naught plus acceleration is CT. So, in fact, that one looks exactly like that one. So what's being said here is in the old method, you came up with S as a function of time. Well, over here, theta is a function of time. So then they came up with S dot. Well, they decided to call it V. It sounds ridiculous because you've already done this in physics and you don't even think twice about this. But then what happens is they decide over here that we need a new symbol for this because we had one for this. So we'll call it omega, and that'll be in radians per second because that's going to be in radians. And then what happens is S double dot is equal to V dot, which is equal to the acceleration. So what they do is they come over here and do this, and they came up with a symbol for that. And so if you look at these two equations, and I know I have them backwards in the fact that if you compare the theta to the S and the omega to the V, you'll see it's exactly the same equation. There's really no difference. So then what he does in the text is he rolls along, blah, 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 blah. And he says, hey, what's the motion of a point? And then he uses a funny diagram, but I guess I don't see the diagram. Okay, well, here's one of the diagrams right here. Anyway, as this blob, this blue blob rotates around, you know that it's the velocity is always tangent to the particle path. And if it's a rigid body, it doesn't break apart. So wherever this thing is, it just rotates around in a circle, which means the velocity is tangent to it, which basically is tangent to the circle. Now, what's interesting, and I'll compare these in a minute, is before we came up with a UR and a UV. I'm sorry, a U theta. And we had those as base vectors. And then we created a polar coordinate system. And what I'll do, I can do this so I can start it twice. Let's see. So I can have two copies of the book open and I won't have to move back and forth. So let me let that come up and we'll go down in a minute. So then he comes up and he says, well, the velocity is equal to just omega r. But then he starts breaking down and he says, oh, well, see appendix B, there's a vector equation associated with that. And the vector equation looks like this. Now, staring at that for a minute makes you think about something. And that is, okay, let me see if I can make heads or tails of this. And that, hang on. Go down here. I got to make a mark so I can go down further and then show up. So he says the velocity is equal to omega r. And he just writes that down. Then he says, okay, that in fact, there's a velocity vector, which is called omega cross r. Now, let's go back to and let's hold our mindset on this for a few seconds. And let's go back to our velocity of A is equal to velocity of A relative to B plus the velocity of B. Now, whatever this is, if you're sitting on an object and it's floating through space, and so here's A and here's B, and I'm going to draw a vector. Okay, in this case, I originate it from B and point it to A. Here's my vector. If I'm sitting here at this point, and this thing is rotating, as it maybe is flying through space that way, the only thing you see at B is a rotation. So this, in fact, and that are the same thing. Does that make sense? So there's no difference in that equation. Those are exactly the same equation. Now you still have a velocity of B. So for example, if this thing were rotating and this is velocity of B, say this is velocity of B, then you would add the rotation component to that. And that's where he's going to end up going to. And hang on, he may, okay, and then he just flops this out on the page. And you're sitting there staring at it, and you're thinking, okay, there's a normal and a tangential here. Oh, I wanted to select everything and trash it. He's got a normal and tangential the same way we did before. The normal pointing from the point back to the center of rotation. The tangential meaning the amount you were speeding up. It's like the car. The AT is your gas pedal. The AN is the steering wheel. As you turn the steering wheel to the left, you'll have an acceleration going that way. But if you shove the gas pedal, you're speeding up as you're going around in circles. So turns out that he has two new terms. So he has a normal and tangential. Then he flops down an equation. Now, this is the way a lot of textbooks write it. But he writes it like this. Now, what we're going to do is I'm going to try to make heads or tails about this, comparing it to what we've seen before. So he will actually come down and I'll do it. Acceleration A relative to B is equal to, looks a lot like the one above. And technically, and actually I should write that omega in front of it. And this is squared, so this is the magnitude. Now, you got an equation like this, and you got an equation like that, and you're staring at it, and you're thinking, how can I make heads or tails of any of this? Is there something I've seen before that I can relate this to? And that's why I tried to bring this up. Now I've got to make my way through, say maybe right there. Nope, a little bit further. Okay, a little bit further. Okay, I'm getting close. Getting close. So instead of me writing it down, I'm going to grab the equation like this one, okay? So use the snippet little thing. I'm going to grab this equation, drop it, say, right there. And then I'm going to go over and get the acceleration, which is right here. And copy it. Oops, wrong place. And I'm going to drop it right there. So from polar coordinates, so if I grab this and put them together, polar coordinates say this, that the velocity vector is equal to, okay, I'll try r dot ur plus r theta dot u theta. And then the acceleration says this. Let me move down a little bit. Acceleration looks like this. Okay, this will take me a minute. R double dot minus r theta dot squared ur plus r double dot plus 2 r dot theta dot u theta. Now let's put this in context. Polar coordinates here's UR, here's U theta, the base vectors, there's R, which in this case, in the case of polar coordinates, the stuff that was written right here, the R could be a function of time. It could change. Now, if you compare this to this, there's one overwhelming difference, and that is, unless the object breaks in a polar coordinate system, R is fixed up here. It doesn't change. It doesn't change in any of those. If it broke, you can't use those equations anyway. So now if R is fixed, then R dot equals 0. Well, so does R double dot. And now you can rewrite these equations. Let's rewrite them. And then you got the velocity is equal to R dot's gone. All you get is R theta dot U theta. And then for the acceleration, what you get, that first term right there goes away. This term goes away. And so all you get minus R theta dot squared UR plus, that one disappeared, so I'm left with that one, R theta double dot U theta. Now this is if R doesn't change. Now I wrote this thing so big that now I'll shrink it down, and I'm going to compare things here. So let's look at this term first. So that term is just omega times R, which if you look at it, that's what that is. There's no difference between those. The difference here is in the implementation, how you determine the actual value. It turns out, actually, I think this is easier to do up here than the polar coordinates. And I'll show you a case in point in a minute. Now, if you compare this one, take a look at this term first, and then look at that term. And what you'll see is those, in fact, are the same terms. And then this term and that term are the same thing. And the R, this is the R, and here's the R. This is the theta double dot, which we've already figured out is the alpha. So those are actually the same thing. These are kind of a subset of polar coordinates which are written in vector form, which means you can choose polar coordinates if you want to, but you do not have to. Now, before I go any further, let me give you a case in point and do it. You know, before I go back to the book, and I don't know what he talked about next, but here, let's look at this. I have an object sitting up here. I'm going to say for the moment, this thing is attached to the ground, and this thing is swinging around, and you could say theta dot if you want to, or you could say omega is equal to 2 radians per second. Now, I can put all sorts of angles on here I want, but let's say I decide I don't want to do that. I just want to tell you what the point, okay, so let's call this A and this point B. And just so I can do it both ways, I'm going to make the coordinates of B be X equal to 4 and Y equal to 3. Therefore, this vector is linked what? 5. Now, I'm going to just find the velocity first. Now, if you're doing polar coordinates, you know, here, well, okay, if you're doing polar coordinates and the R doesn't change, I can grab it right there. Velocity is equal to R theta dot U theta, which I've got to figure that thing out, which is equal to what? 5 times 2, or it's a value of 10. But that's not the complete story. You've got 10, and it's in this direction. And unfortunately, oh, I know how I can do it. Let's do it like this. Move that over to the side. Oops. Well, unfortunately, this is my u theta here. So there's my u theta. I know that direction. Let's do it in this other way. The velocity of B relative to A. Now, I already know, if I want to know the velocity of B, I already know what's the velocity of A. It's gone. Now, this equation is telling me it's omega cross R B, relative to A. Now, whoa. If I just, now here's where you got to start using your right-hand rule thing. What is omega and what is the other, the RB to A? And I do it this way just because I like to do things kind of regimented, always the same way, so I don't have to think a lot. Now, in the book, he does something different, which we'll talk about in a minute. But if I put omega in there, this is something you have to be very careful of. Now, a physicist is very, very meticulous about this. A rotation, right hand, stick your hand on X, rotate it to Y. This rotation is positive. So this is positive omega. Or it turns out it's 0, 0, and 2 because I was given the 2 right there. So technically the vector should be 2k. Does that make sense? And that's something you have to get used to. When there's a moment or a twist or a movement in angular, you use your right hand and your thumb points in that direction. So in a plane, if I took this and twisted it, the twist would be in that direction. It doesn't make sense, but if you think about it, that's the way they classify this. Or maybe it does make sense. It makes sense to me because I've done it so often I don't question it anymore. So then the next question is, what's the RB to A? If you just look at the vector, well, it's just, let's see, 4I plus 3J, right? So that's a 4 and a 3 and a 0. Then I break it down like this. Okay, what's that called? Cofactor expansion. You could do it that way. 0, 2, 3, nothing. Minus, because it's you're taking the second one. 0, 2, 4, nothing. And then plus K. And by the way, there won't be a K. Because you always get a 0, 0, and then I don't care what you get there, and I don't care what you get there, because the 0, 0 will cancel it out. So what you end up with is the velocity of B is equal to 0 times 0 minus 6I plus 8J. Did I do that right? Now let's see if this makes sense. Okay, I'm going to redraw this thing. Sits here about like that. It says I go backwards, value of 6, and then I go up, maybe a little higher value of 8. I cross this, and it should be in the right direction. Now the question is, okay, so this shows the magnitude of that thing is supposed to be 10. Let's check that out. So is the square root of 6 squared plus 8 squared 36? What's 8 squared? Yeah, so that'd give you 10. So it's equals square root of 100, or the magnitude of this thing is 10. So the magnitude's 10. Now what you just did, to me, in a way, you've backhanded this thing by using polar coordinates without explicitly ever setting it up that way. That's where he's going to. I don't know how long it takes him to get there in the book. So he starts here, okay, and it turns out the acceleration does the same thing, but we'll get there in a second. So he goes on. Oh, and then he just starts working problems. So he works problems and works problems, and then maybe he has more problems. Okay, he lists the equations out there, and he breaks them apart, tangential and normal. I keep them all together. So then he's working problems. So he doesn't go anywhere. He just starts working problems. So maybe we should join him, although before we join him, let me make sure we kind of understand that's where we're going. So the most important part out of here that you're going to see later is this equation gets repeated over and over and over and over and over, as well as the velocity equation. So, but this way, by looking back at what you saw previously, you realize that what you're doing is you're just saying in a rigid body situation, the 2 points don't move away or towards each other. So the polar coordinate system breaks down to something like this. And in fact, this and these two, well, yeah, this one is appropriately, the velocity is equivalent to the velocity and the acceleration is equivalent to the acceleration. So in fact, you've seen this before. And so let's go work a problem or two. And I said that I'm going to go, homework set 3 is in chapter 16, and it didn't have numbers associated with it, problem numbers. So I'm going to go back and change that set so that it has the numbers so you can look up the answers without, too much hassle. So here, let's just pick one. Let's see. Well, he doesn't have any. Oh, yeah, he does. Okay. So here, the gear rotates 20 revolutions. It achieves an angular velocity that, starting from rest. Okay, now this is just starts from rest. Determine the constant angular acceleration and the time required. This is dumb. But anyway, I'll do it. See, that's what I get. I usually am not. Okay, let's add a page and let's do this one, although it's stupid, but Okay, it rotates 20 revolutions. Oops, wrong thing. It rotates 20. Well, if he's saying it's the constant acceleration, I guess we could do this. Let me just write the equations. I'll go back and determine what it is I'm going to deal with, plus what goes here. Is it omega t? What goes here? Is it alpha and then t squared over 2, right? And of course, he gave us that. Now, if I wanted to go, I could do this. Omega is equal to, I should say naught right there, sorry. Plus alpha t. So I got those two equations. So he says it went through 20 revolutions. Well, okay, 20 revolutions, and then there's 2 pi radians every revolution. Meant the thing, and he said did it start from rest? I hope so. So if it started from rest, that goes away. Okay, so now I'm going to assume achieves angular velocity. I'm going to assume this one's gone away. So now I've got this. Omega is equal, theta is equal to omega naught t. Well, if it starts at 30, what is omega naught? I mean, if he says you have a constant angular acceleration, so he said it achieves an angular velocity of that. He should say, I'm going to assume that it reached that at 20 or whatever this number is, 40 pi? So at 40 pi, it equaled that, right? Wait a minute. Yeah, but wait a minute. I should. He said it started at rest, which meant, and I'm assuming it started there. I reached. But if you assume that's gone, wait a minute. If it starts from rest, wait a minute, I forgot my other term. Sorry about that. So you're at that. You have no. Okay. So I wrote that down. Why did I not write this other part? That's wrong. Plus alpha t squared over 2. So alpha. So then the question is what else do I have left? Now I've got omega is equal to alpha t. So that shouldn't be there, but this should be 30 is equal to alpha t. And that. So I got this one. This is just superly annoying. I got that one and that one. And I don't know alpha and I don't know t. So which one would you want to do? Would you want to solve for t or would you want to solve for alpha? If I did alpha is equal to 30 over t and shove that back in there, I get 40 pi equal to, put an alpha in there, I get 30 over t, t squared over 2. Did I do that right? Do what now? And then 15, now I don't know what that number is. I can't go down. Okay. So that's 15t is equal to 40 pi. I don't know. T is equal to 40. I thought that maybe it would be like an integer, but I guess I'm expecting too much. Wait a minute. Okay. Well, I guess I'll do this. Do command line. Oh, good. Okay. Let's see who wins. 8.37 or 8.4. How about 8.4? Luckily, I have this one up. If I swim to the back of the book, oops. I don't even know what problem I just did. Was it? Okay. Okay, so I did it backwards, but I 8.38. That's what he got. Okay, so I think that's what I got. 8.38. Yeah, so 8.4. And then you go in, and I guess you're trying to find alpha. So then you just take this thing. Alpha is equal to 30 over 8.38. 8. So I'm just going to assume I get the same answer. That's a dumb problem, but it's working off the concept of the constant angular acceleration. And at first glance, that might not make good sense until you realize, just like a force, if you flip the switch on an electric motor or something like that, usually, not always, but usually it'll try to supply, well, it'll try, but it probably won't make it to supply a constant torque to it. And so that constant torque, if the fact that has the rotational inertia is constant, it'll produce that. It'll produce a constant angular acceleration. So unfortunately, oh, what are we doing here? Yeah. Okay. See you next time. Or I'll see you later at 2:00 if you want to come again. Who's coming again?